Today I want to, everything I'm talking about today is joint with paper called Wedrich. The paper I'm going to be talking about is out of the archive, but there's actually some new stuff that we kind of figured out since then. Some bonus stuff that I can tell you closer to the end of the talk, having to do with the heights we expect from the Temperley-Lieb category. To understand, well, to sort of motivate and appreciate the context of my talk, so I want to start with just a brief introduction on the subject of quantum non-invariance. Oh, by the way, I haven't turned on my mic. Can you hear me?
Turn it on.
Is it on? Oh, it is on.
It doesn't.
Okay. So quantum non-invariance, which I think is really beautiful interaction between low-dimensional topology and representation theory. Specifically, so there's a whole bunch of families of quantum non-invariance, specifically ones I'll be talking about. It's not important, but they're interested in naming things. These are called directives of invariance. And the input for this family of invariants is a complex semisimple algebra. You should think like SL2 or SLN. In this talk, it'll be SLN. And a representation knots. Whenever I draw knots, I'll always draw them by their two-dimensional projections. No, there's the right. And the output of the construction is a polynomial. But I'll just sort of write it as a so it depends on all the data. So it's really a round polynomial cube, but I'm going to write it as if it's just a rational function, just for simplicity. And this construction satisfies a number of properties. For example, you fix the knot and representation splits the direct sum, and the corresponding invariance will add. The other thing you can do with representations is you can center them. And this corresponds to a cabling operation on knots. So let me just sort of write this, try to draw a table. So I've drawn now parallel copies of my knots, and one of the copies should carry the representation B, the other one will carry the representation W. And let me just sort of correct a small lie that I told you at the beginning. K should really be a framed knot because we need to be able to form parallel copies, and I need to know which parallel copy to take, and then it's determined by a framing of the knot. And furthermore, it makes sense not just for knots, but for links of our components. Anyway, and just one more little property that is kind of interesting. So if your knot is the unknot, then the corresponding invariant is some kind of dimension. I'll just say maybe like a quantum dimension or a greater dimension, that representation. So again, this is another sort of slight lie. So V should really be thought of as a representation of the quantum group, and this dimension is the dimension of that quantum group. So for example, for SL2, if your representation is the irreducible representation of highest weight n, then its greater dimension will be quantum integer n+1. Okay. sorry, my picture is in kind of a bad place. So ignore this picture for just a second. Now, so the sort of aspect of this that I want to focus on is if you fix the knot and let this representation vary, you get a linear map. So these quantum invariants should be thought of as linear maps, really, where the input is the representation or possibly a formal linear combination of representations. So this is the Grothendieck group of graph G. And then the target is thermal polynomials or rational functions. So in the case G is SL2, this is recovered from donor polynomial and it's colored what we call the color of Jones polynomials. So the irreducible representation of wave 1, well, that's just this will map to don't polynomial A. And in general, the representation of activate N, that's the symmetric power, that maps to what we call the N color Jones. Okay, so that's an old story. This is the sort of story people were working on in the 80s and 90s. Too many people to list here. So the role of this representation ring, K0 of the category representations, we call this is called the skein module of the analogous. Maybe in the interest of time, I do want to write it. We're going to categorify all this stuff, and so it's useful to know what we're categorifying, right? So the sort of topological description and sort of the key to this relationship is the following little fact. So for the rest of the talk, G is just going to be SL2. So the representation ring of SL2 is pretty easy to describe, but it also has this sort of topological description, which is you take the vector space spanned by all link diagrams in the drawn in the analogous. So my analogous, and then I take sort of all possible link diagrams. I'll draw a very simple one. Yeah, but you take all possible link diagrams, formal linear combinations of them, then you impose some local relations, often graphic relations. So one expresses a crossing in terms of no crossings, the other just tells you the removal of a circle. Multiplies that diagram by. Okay. So I know this is maybe a little bit more motivational resurrection, but it's useful. So one of the reasons this is really cool is because you can actually use these knot invariants or link invariants to build free manifold invariants. So the relationship between knots and free manifolds, I'll just sort of summarize in a very big black box. So there is a construction called surgery or Dane surgery, which given a parameter length will produce a free manifold. In fact, every closed free manifold has a surgery presentation, and there's a complete description of the kernel. So you take frame links. Many of you have seen this before because it's very standard, but maybe possibly some of you haven't. So we're saying the kernel is described by these moves on these additional moves on link diagrams. So you have not only the right-Meister moves or whatever the frame right-Meister moves relating, these diagrams, but you also have the following. So this is a -1 framed unknot. You can delete a -1 framed unknot at no charge. You can delete a +1 framed unknot also at no charge. This is called the blow-up move. And then there's another move called the handle slide move. And the handle slide move is this move. It says that so I choose a component of my link, say this guy. And then I choose an arc of a nearby component. It doesn't have to be completely disjoint, but it just is some arc of some component which is different, which is nearby. And the handle slide move slides this red arc over the blue arc, or the blue circle, kind of this way. You should imagine the surgery construction will produce a little disc bounding that blue, and you're sliding over that disc. Okay, so the key, the point is that you can attempt to build pre-manifold invariants by building link invariants that are invariants under these additional moves. Okay, so it's a kind of a huge problem to build link invariants that are invariants under. This move is something like a normalization or non-degeneracy on your link invariant, and this move is really sort of hiding. They're both not true, but this one is close. And so the point is that there is actually an element in this representation ring, which, when you sort of color by it, you get a handle slide invariant. You get a link invariant, which is further invariant under handle slides. That's called a Kirby element. So there's a special element. The Kirby element. Call it omega. And this is the sum. So I'll say it's the sum over all irreducible representations of your group, or your algebras, so SL2 in our case. And you take the class of that representation in your group, weighted by its dimension, or rather its greater dimension. And that's an element of the representation ring, or zero graph. Okay, this is actually kind of a big lie, because this is an infinite sum and this is total nonsense. So in order to make it finite, you need roots of unity and semi-simplification. So it needs Q to be a root of unity. I'm going to completely ignore this aspect of the start, because this is still purely motivation. Okay. When we categorify, we will completely ignore this condition. Therefore, the object we get will be some huge, it'll be an end object of whatever category. It'll be in some kind of analogous way. Awesome. Okay, and this Kirby element is special because so if I draw my pictures in the annulus, the thing that makes the Kirby element special is it satisfies handle slide invariance, which I'm going to state the handle slide invariance kind of in the following way, which turns out to be. So I draw my Kirby element kind of as a formal little diagram in the annulus. And the point is, this looks like a special case of the handle slide, but in fact it's equivalent to handle slide, morally speaking, anyway. So if I took sorry, so I'm getting myself into a logical pickle. So if omega were invariant under handle slides, then I could slide a piece of this arc off of omega, and I would get a picture like it's like sort of half of this loop. You could do a handle slide loop. And then now I have a trivial little closed unknot. This could itself carry some kind of representation P. And now I have a little closed unknot colored by the representation P. And that's, remember I said the deletion of I guess, and more generally, the deletion of B colored not should induce the multiplication by the graded dimension of B. Probably should have written that. And then, so this is the graded dimension of B. So we're not all of us are topologists in science. And so the kind of slide move algebraically, it has a kind of an algebraic avatar, which is simply the following. So the Kirby element is an element of the representation ring that satisfies this kind of property. So it chews on, it eats representations and spits out their graded dimensions. So in this way. So that's, and it should be non-zero. I mean, obviously the zero element has the same kind of identity, but you want the Kirby element to be some sort of non-trivial element of the representation ring satisfying an identity like this. Anyway, it turns out this is equivalent to the handle slide property, and that gives them 3 manifold invariants. So that's the whole story. If you want to categorify it all.
So the 3 manifold invariant depends on the choice of unity.
The 3 manifold invariant would depend on the choice of grid of unity. Yeah.
Can you get around that by working that in the completion of the Grothendieck?
No, I mean you can get around it by working, I don't know, by working like heroes or not. I mean, there's other ways of getting around the specific choice of unity. You could work with like all roots of unity kind of simultaneously, but you do need. Okay. So this is what we're going to categorify. Guess I'm over here now. So in categorification of this story, so the Jones polynomial, that's the non-invariant that we're actually working with, sort of, gets categorified by a homotopy. Again, this is still part of the black box, and then assume that we're repeating these same slogans. So the Jones polynomial is categorified by this quantum homology. So the quantum homology or not should be thought of as just a doubly graded vector space. So I'm going to write it as GPG vector. GPG vector is going to be the category of doubly graded vector spaces. The category, the ring of coefficients, really everything can be done integrally. So this gets categorified by chain complexes, or I'll say doubly graded vector spaces here. So GG vector is this sort of target of all our invariants. We categorify. And how do we categorify the representation ring of SL2 rep? How many of you want to put SL2 rep here? Obviously, rep SL2 categorifies is all the Grothendieck group. So why not? Do it. It's actually the wrong thing to put here. For kind of reasons that there is a point. Anyway, but so this is actually the wrong thing to put here. But so rep SL2 has this Temperley-Lieb description. So rep SL2 is equivalent to it's equivalent to the additive item completion of this Temperley-Lieb category. And the actual correct thing to put here is not the Temperley-Lieb category, but rather the data Temperley-Lieb, which is abbreviated. Okay. And so the statement is finally that quantum homology and all of its tables give you a function DTL into the GG vectors. And really the point of what I'm talking about today is we can construct an object, or really it's an end object of this category. So again, I'll call it omega. So it's just an end object in this DTL thing. I just think of it as like an infinite union of objects in this category, which has the property that if you tensor with, so this is a monoidal category, and you have a tensor with this thing, then you get some sort of categorified graded dimension. But let me pause for, let me rewind for just a moment. The unknot, if you have an unknot here. This in an object of the DTL category here would denote this just by default of X. This is something like a polynomial representation of DTL. So that's some graded vector space or fellow graded vector space. And it has an analogous property. And we prove that this property holds for our object, and then that is, implies some sort of the correct analog side invariance. But amazingly, it does not categorify this formula. And so, so this is like the original definition of the Kirby color. When I give this talk, like in front of topologists, they always ask the question: do you categorify that equation? And the answer is no, not at all. And it's a little weird, but I want to hopefully put this into some light. We don't categorify it. It's fun. So the goal of my talk, I want to introduce the category DTL and tell you what this Kirby object looks like. And I'm sure I'm going slower than I intend to, but I'll show you what this category looks like, or what this object looks like, and maybe give you a version of a formula kind of like this that made me happy. Maybe it makes you happy.
What happens to the blow-ups? Is it obvious that
blow-up's going to be completely not satisfied. Yeah. So actually the invariant, okay, so the motivation for categorifying these things is, or really maybe possibly categorifying anything. So categorification as a subject in itself was born in 1994. So Crane and Triangle sort of prophesized that the categorification of a three-manifold invariant should produce a four-manifold invariant in some kind of concrete way. And I say prophesize because it's really kind of over. See, a lot of what we do these days is motivated, or like the origins can trace back to that kind of thing. And so if you don't include this blow-up condition, you get something which is more closely related to a four-manifold invariant. So that's actually okay. The blow-up move is not satisfied by your invariant. Okay, so I will not say anything more about that tonight.
I think this is the last thing he says. Constructing a three-manifold invariant or four-manifold?
So in a more topology leaning audience for the topology leaning talk, I would say the following words. I would say there is a four-manifold, there's an invariant of four manifolds called the skein lasagna model. And what we have is an algebraic description of the skein lasagna module of a two-handle ladder. So a framed link could be thought of if you're three-manifold. A framed link could be thought of as giving you a three-manifold. But it also gives you a four-manifold bounding that three-manifold. A two-handle ladder. So you take the force here and attach two handles to it until you get a four-manifold whose boundary is your prescribed three-manifold. So the invariant we reproduce is in fact not an invariant of the three-manifold, but of the four-manifold to boundary. That's related to this failure of blow-up. Okay. Connect something with CP2 or CP2 bar in the interior doesn't change the problem, but it does change the form. Okay, section 2. We're going to talk about, it's like DTL is. So DTL has objects the set of objects is going to be just a set of non-negative integers. We visualize these things as dots and lines. Morphisms. So the homs from n dots to m, sorry, n dots to m dots in this category is going to be, let's say, linear combinations of diagrams, like Temperley-Lieb diagrams, with dots on them. So if you've seen Temperley-Lieb diagrams, you can pretty much imagine what dots on them. So the Temperley-Lieb diagram is just a planar kind of matching of n points on the bottom with m points on the top. And the strands are allowed to carry some dots. They don't have to, they can carry 0 or more dots. And then the relations that we impose are, so first off, the relation of a circle is, so is not 0 equals to, that's not equals to. A dotted circle evaluates to 0. 2 dots on the same strand are 0. And then there's one more kind of strange looking relation, but here it is. The relations themselves are actually not super important, but here they are. So this is the dotted Temperley-Lieb category. So one thing that's sort of clear is that there's a map from the legal Temperley-Lieb category into here. There's a functor from the legal Temperley-Lieb category of equals 1 to the dotted Temperley-Lieb category, and this is due to the isomorphism of Grothendieckers. So they both categorify the same thing, but they're different categories. And the functor here, let me just sort of say vaguely that the functor that I'm describing here fixes a knot, and the functor sort of induced by taking the bottom homologies of various cables. Okay, so it sends the object, which is like n labeled dots. It sends an object to the bottom homology of the n cable. I'm going to write briefly just in this market. This is the bottom homology here. And then on the level of morphisms, it sends like this generating diagram to the covariance map induced by the K-pan covariance. So, in the interest of time, I'll only say this sort of vaguely. You see, if you've seen the bottom homology, then this makes sense. If you haven't, then I'm not going to make it make sense today. But there's some natural maps to these pictures. And then the dot gets interpreted as a dot on a strand gets interpreted as, so just a single vertical strand is the identity covariance. It's the identity map, but placing a dot will attach a handle at some location on that whole sequence. And then this relation, this funny looking relation, is just a consequence of the what we call the Barnaton net conversion. Okay. So what you can think of is dotted Temperley-Lieb has something to do with like SL2 representations, but you might think of the dot as being like multiplication by E or F in SL2. So you get a category of like whose objects are like SL2 representations, but whose morphisms are no longer SL2 equivariant because they include like E itself as part of it. It's allowable morphism. Okay. So, any questions about the dotted Temperley-Lieb category? Yeah.
Does the FNLP basis just by full diagrams later?
Do the morphism spaces have obvious spaces?
Yeah.
They I don't know that it's obvious, but yes, they do have a basis. So there's a duality. So yeah, so that's a great question. So hops from the empty guy, from like 0 into n, or n should be even for this to be non-empty. So hops from 0 into 2n has a natural basis. Yeah, it's a great question. So what you do is you take the usual sorts of basis elements that you see in Temperley-Lieb, and then you allow your dots, but your dots should be at the very bottom of your. They should have a viewpoint to the bottom of the little square. So my basis element. This is the basis element. That's the basis element. This is the basis element. This is the basis element. But I'm only allowed to put dots on the pieces of my diagram which see the bottom edge of the square. So the relation that I erased allows you to migrate all the dots to the bottom of the diagram. And you can see that the dimension of this thing. So previously you would compute the dimension of this sound space. The usual Temperley category, this would be a Catalan number. In this category, so this is a good time to say that morphism spaces in VTL are Z graded by the number of dots. And so we can talk about the graded dimension of the sound space. And this turns out to be equal to the dimension of the cohomology of some 2 rows Springer fiber. So these things are kind of like related to other objects that you see in the dimension representation. I won't write that because I'm not. So sort of lots of things planned to say, and I don't have time to write them all. So the dimension of the cohomology 2 rows Springer fibers. That's a fun exercise. Is it homology or homology? It might actually be homology. Could be homology.
Dimension is the same. Great dimension is the same.
I mean, but if you want to honest equality, not equality, I'd say Q goes to Q inverse. Whatever. You're right. It's kind of inconsequential. Another comment. So this category, I know it appears totally random and ad hoc, but another comment. This category appears in geometric representation theory. This is also isomorphic to big SL2 equivariant sheaves on a Hilbert cone. So this is the sort of thing that appears in geometric stacking. So if you guys care about that, then this is also the sort of category you might care about. So it's related to lots of things. Okay. So the next goal is to build an object. So I'm going to tell you how to construct them later. What we need is an analog of the indecomposable objects. So we need an analog of the Jones-Benzel projectors. So all we have is an additive category right now. It's not item complete. So we first pass to this item completion of our Kirby envelope. So this omega is actually going to live in. It's going to be an end object, so it's like a formal nested union of things or whatever. In the end objects in the Kirby completion, or maybe the additive completion. So you take the Kirby completion of VTL, and you throw in all direct sums and you throw in all graded shifts. That's what our guy's going to live in. but we need the indecomposables in this category. So let me talk about those. Okay, so the object, so it's going to get kind of tedious to write these little dots all the time. So this object, we're just going to denote this v to the tensor power n. No, just like rep SL2 is monoidal, this category is monoidal. The monoidal operation is just placing diagrams side by side. And so you think of n labeled dots is just the n tensor power of the one labeled dot. That's how we call them. This guy has an idempotent acting on it, a projector acting on it, which is an analog of the nonzero projector. And I'm just going to and so you think of the nonzero projector. Let me just say this is really just the symmetrizing idempotent. It's the symmetrizer, where the symmetric group action is determined by the equation. So it turns out there's a symmetric group action on this object, which is kind of induced by this sort of addition. Anyway, so you take the symmetrizer written as a morphism in our category. This is like a usual Jones-Bendel projector at q equals 1. And I'm going to define capital P sub n to be the image of that idempotent in this Kirby completion, in this idempotent. So in the ordinary Temperley-Lieb category, that's the category semisimple, there's no morphisms between your indecomposable objects. There's no Homs between distinct irreducibles. These are the objects that represent the irreducibles. Think about it as SL2 representations. But in this category, there are morphisms. So let me just give you an example. So P0 is just the monoidal identity. That's the same thing as 0 dots on a line. P2, the object P2 is the image of the second Jones-Bendel projector. The second Jones-Bendel projector is, oh, I said symmetrizer. Maybe I meant anti-symmetrizer. I don't know. No. Yes, symmetrizer. So P2 is the image of this idempotent acting on the second tensor power of P. And there's a relation in the Temperley-Lieb category that all possible ways of closing up the Jones-Bendel projector give you 0 morphism. But now if you have dots, you actually get some non-zero things. So this actually represents a non-zero morphism. That represents a non-zero morphism from the sort of second symmetric power to the 0 symmetric power. And in general, you have all sorts of morphisms given by dotted cups or whatever. From E to N to E to M. Sorry, to be from E N to E like N minus R. Okay, so you have all kinds of morphisms in this category. I can give you a definition, but it's not going to be totally obvious why it's the right definition. No. So I wanted to find my Kirby color as like an infinite symmetric power of E. And how do we define infinite things in that? Well, we define infinite things as limits of finite things. Well, in category theory, in order to form a limit or element, we need to have chosen embedding of like one thing into the next, so that we can say like in some acceptable way. So I want to define the Kirby color as an infinite symmetrizer, like a P sub infinity. But I need to express anyway, so I need to direct the system so that I can take a limit or a element. That's what we're going to do next. When do I go and when am I supposed to stop? I didn't record the time.
I think you sound about 22.
Hmm?
Yeah, 45.
45. Okay. So I should stop at
10 minutes.
In 10 minutes.
in 10 minutes, okay. So the Kirby color that we actually define, Kirby obviously defined. So there's an even one and an odd one. You see there's a parity kind of constraint. There's no morphisms between N and M unless N and M have the same parity. So I have two different directed systems. And two different co-limits. So one directed system just takes this guy and maps it to the next one and maps it to the next one. And all the maps here are these dotted up maps. So sorry. Just to make these degrees 0. So the dot, I didn't tell you exactly how these morphism spaces are graded, but we give the dot the degree 2. We give the dot. In order to make this a degree 0 morphism, I should shift this one down a little bit. So my gradient shift functor is going to be called Q. Anyway, you can ignore these if you want. And the other one is same sort of thing, but starting from 1. Maybe inverse 1 and 2 minus 3 and so on. So these are our Kirby colors. The Temperley group is that these got so these live in what category? They live in the incompletion. It lives in some kind of prototypification of these guys. So you take a Kirby on book, and then you adjoin their sums and you join just, and you would join the limits. And the theorem, so this is still a middle category, given it's under. The theorem is that inside that category, our Kirby guy, and then the unlabeled Kirby is the direct sum. So the theorem of me and Rose and Wedrich is that this guy, this Kirby color that we define, has that sort of property. So if you tensor an object of the DCL of the data type category with omega, which you end up with is isomorphic to this thing that I had called Paul. So it's the categorified analog of Kirby color tensor field representation producing a great dimension of error. And I'm thinking about SL2 representations, what Paul does is it takes the underlying vector space. It forgets about the SL2 action and just takes the underlying vector space graded by weight space. So X is an object of the data type category, which can be thought of as like the SL2 representation. W, then Paul should be thought of as the underlying graded vector space. So this is the theorem. The consequence of this is coloring by omega. So omega gives sort of like handle slide invariance colored von Neumann. So omega colored von Neumann is handle slide invariance. Really not obvious from the definition, but in fact, it works. Just a word about the proof or the construction even. So the idea for the construction came about by just Kirby and his student H2 Megalab wrote a paper sort of they gave a paper they wrote on like, what effects the addition of a 2 handle has on scaling Zanya module or whatever. And so reverse engineering what they wrote down kind of gave the inspiration for these problems. So they do come from somewhere. Now. So maybe I won't really have time to again, give any justice for this, but I'm going to say the buzzword, which if they pique your interest, we should talk about it. Another thing that I was hoping to tell at least some of you guys was that there's actually a diagrammatic presentation of this category. So the data Temperley-Lieb category is this very attractive like diagrammatic presentation. You can adjoin this Kirby color to it. You get a new homotopy category. It's data Temperley-Lieb stuff and this Kirby on it and power units have the Kirby on it. One of the interesting things one of the interesting structures that this Kirby guy has is it's an algebra object in the category. And it's actually a quasi-idempotent algebra object. So if you square it, then the result is isomorphic to a big direct sum of copies of itself. And with some shifts. And there are some, it's infinite, so to tell you what that means, this is really actually a byproduct. So there's really like an idempotent decomposition of the identity. So in our little graphical calculus, we have red strands representing the Kirby guy. There's an idempotent decomposition of this guy using the algebra structure and some other stuff. There's an explicit idempotent. So if you're into diagrammatics, we should talk about this. And the kind of diagrammatics is a little bit weirder than you're used to because there's no infinite sum. You have to figure out how to make sense of that. But I promised to say a little bit something about this high-space structure. So let me just like very quickly say how this it sheds light on this formula, on this weird-looking formula. Okay. So there are standard objects. So I'm gonna. Those of you who know me well are probably thinking like, man, you're not yourself. There's no crazy homological algorithms. Where's the complexes? Here's the, well, here they are. Okay, so we're gonna pass from the, we're gonna forget about like incompletion or whatever. We're just gonna look at chain complexes. So the DTL category, we'll look at chain complexes in the Kirby envelope of ETL. So throw in all direct sum hands, throw in all sums, throw in all two shifts, and look at finite complexes built up out of them. But this thing has something like a highest weight structure, at least up to homotopy. Let me tell you what the standards and the costandard look like. So they're indexed by natural numbers. The costandards, this is coming, well, maybe it's part of the inspiration for this is coming from this relationship with these categories up here in Satake. Thank you, Nice for patience. So anyway, so these complexes, there's little two-term complexes. So there's the space of morphisms in this degree is one-dimensional. So there's a unique kind of size-morph with a unique chain complex like this. And his dual, this is dual morphism. Dual chain complexes like this. These are the standard and costandards. And we interpret, negative numbers as 0. And this so we have these funny looking complexes, and these satisfy the usual things that you would expect from the highest weight category. So Ham's from a standard dude, and what I'm claiming is a standard guy. So a costandard is contractible if n and m are not the same, and it's isomorphic to it's not the ground field exactly if n and m are the same, but it's this algebra. If n and m are the same but also not 0, and then the special case Okay, so but anyway, the orthogonality property of these two things is very reminiscent of a right-split structure. And if you guys are really curious, the tilting on anytime you have a highest wave structure, your first question, what are there tiltings? Are there enough tiltings? I don't know. Maybe you guys know about that stuff. But I know a lot of people here think about stuff. So what are the tiltings? Tiltings are these kinds of weird complexes. Little diamonds. You guys can have fun with this if you want. These little diamonds. So the nth tilting is a little complex like this. These guys are in nonzero. And the maps are the only ones that can be cosine. And you can see it's like standard filter and cosine filter, blah blah blah. Super cool. Anyway, this expression, this infinite kind of expression here. So here's a little sort of claim. There's an infinite complex you can build. Where I take the zero kind of costandard, then the second, and the fourth, so on. These are going to be homologically degree 1 maps relating these things. So that when you take the sort of total kind of complex represented by this, you get something that is equivalent in an appropriate sense to this Kirby color. This is an expression for the even one, the odd one will have a description. And the way you see this is very kind of attractive. So the costandard 2 looks like this, the costandard 4 looks like this. The mass between them that project included, I don't know. There is a T structure. Yeah, exactly. There is a T structure that I'm hiding, but it's like similar to what you would expect. It's like perverse complexes or complexes situated in with like slope 2. So if I include the gradient shifts, this is going to be a Q squared. This is really Q to the -2. I'm sorry, maybe I misunderstood the question. So this should be considered to be perverse, or it's in the heart of our T structure. And each of these is actually not in the part, so there's really shifts here. So it's kind of really a proper complex. The resolution of our. There's no shifts here, yeah. You can see the map, it's the projection followed by inclusion of it. Anyway, so the point is, there's this sort of resolution of the Kirby color that using these cosine guys. And I'm really out of time, but I hope somebody asks me for a topological picture of the cosine standards. Like, all right, thank you guys.